This review is for people who already know how to program in C to some degree. If you haven't used C for very long, or not used it in a while, this should help you get up to speed. After completing the review, you should be comfortable using the tools for developing C programs. To get the most out of the review, follow along with all the activities. You will need to use a Unix distribution and the terminal. Make a directory called source. Nano is an easy-to-use editor. -W tells it not to wrap long lines. -L tells it to show line numbers. -Y none tells it to turn off syntax highlighting, which makes the code easier to read in the video. Hello World is a traditional introductory program. Number include makes the printf function available. The main function is a starting point of the program. Main is called by the operating system when the program runs. argc and argv are how the program receives command line arguments. Printf displays something on the screen. Printf doesn't add new line characters at the end of the lines automatically. You must add a /n anytime you want a new line to appear. Return 0 tells the operating system that the program succeeded. Using 0 to indicate success is operating system dependent. Some operating systems could use a non-zero value to indicate success. I focus on writing C programs that can run on various operating systems, so 0 probably indicates success is not good enough. The standard lib header file makes the exit success macro available. The standard library that ships with a compiler or operating system sets the value of exit success to the appropriate value. By using exit success instead of 0, the program is now portable to more operating systems. Configure Nano with the .nanorc file. Configure Nano so that it always shows the line numbers. Save and exit, and then rerun Nano without the -L flag. The line numbers should still show up. You can use man to see all the configuration options. This version of Nano doesn't require -W anymore. You can customize the syntax highlighting. You successfully customized Nano. A function is a group of instructions that should perform a specific task. Each function requires a prototype. A function prototype is needed to ensure that the compiler knows the number, order, and types of parameters the function takes and what type of value it returns. This function is named displayMessage. DisplayMessage takes no parameters and returns no value. It is important to break code up into well-defined functions. Well-defined functions are usually small and focused on a particular task. Being focused makes them easier to write, easier to read, easier to test, and easier to maintain. A compiler converts human-readable source code into instructions that a CPU can execute. A programming language, such as C, allows programmers to work at a higher level of abstraction than machine code or assembly language. Without a language like C, programmers must rewrite their code for each hardware platform and operating system type. C is known as a cross-platform programming language. A platform consists of the CPU, operating system, and compiler. C makes creating code for multiple platforms relatively easy, while still giving programmers access to low-level platform features. Working at a higher level makes programming more accessible, understandable, faster, and less error-prone. A compiler typically consists of several phases: lexical analysis, which breaks the source code into tokens; syntax analysis, which verifies that the tokens have the proper structure; semantic analysis, which confirms the correctness of the code; intermediate code generation, which are the initial instructions for the target CPU; code optimization, which aims to make the program run faster or take up less space; and code generation, which generates the final instructions for the target CPU. The compiler also has to manage variables and functions, collectively called symbols. The compiler produces object files, which contain the CPU-specific instructions. The linker brings all of the object files together into a single file called a binary. If the binary has a main function, it's a program. If it doesn't, it's a library. Libraries can be static or dynamic. A binary contains all the functions in any static libraries it links. A dynamic library is linked at runtime by something called the loader. For example, printf is part of the C standard library, a collection of all the functions defined in the C standard. Suppose printf has a bug and the standard C library is updated. Once the library is updated, any binaries that dynamically link it immediately get the bug fix. Static libraries require the binary to be relinked by the linker to get the updates. Any program that statically linked the library will not get the fix to printf until it is relinked. Programs that use dynamic libraries automatically get any bug fixes or speed improvements when the libraries are updated. Static libraries provide more control because you know exactly how the code behaves, but they result in larger binaries. Binaries that use dynamic libraries are smaller and can immediately take advantage of fixes without any extra work. There's no right or wrong answer on which library type to use. Which type of library you pick depends on your needs for a particular situation. When a user types the name of a program, the shell finds the binary on the file system. The operating system then uses the loader to combine the binary and any dynamic libraries it uses. Finally, the main function is called, and any arguments typed by the user are passed to argv. GCC is an open-source compiler available on many operating systems. GCC works with several languages, including C. First, run GCC to see if it is on your system. If the system does not have GCC installed, you may see a message like this, and you can install it. If you don't have it, and your distribution doesn't give you an easy way to install it, you will have to install it by hand, which is specific to your distribution. Make sure that GCC is installed. GCC requires one or more files to work. By default, the binary file that GCC produces is called a.out. Run a.out. You should see Hello World displayed on the screen. To change the binary name, pass the -o flag and give it the name you want. Now run hello. GCC can generate several transient files. It is safe to delete transient files because the compiler can recreate them from the source code. To see the generated files, pass --save temps. The .i file contains the results of the preprocessor. The preprocessor alters the source code before the lexical analysis phase. For example, the preprocessor adds the contents of each number included file. Notice that the return changed from exit success to 0. The .s file contains the assembly language from the code generation phase. The .o file contains the binary instructions for the CPU. Reading a binary is not easy because it contains non-printable characters. Use the od utility to view the hello-main.o file in octal. Pass od the -c flag to view the file as printable characters or decimals. Notice that you can make out a few words. Use the strings utility to extract readable content from a file. The nm utility shows the symbols in a binary. You can see that hello main.o has the display message, main, and putS functions. The number to the left of the function name is the virtual address. A virtual address is an address given to the function by the compiler. The virtual address will get a physical address when the operating system creates a process out of the binary. T means that the symbol is in the text or code section. U means that the symbol is undefined. Seeing putS is odd because the source code doesn't refer to putS. When you call printf with just a string, GCC replaces it with a call to putS, which is faster than printf. PutS is also part of the standard C library. GCC has told the loader that the putS function is needed. The hello binary has more symbols, which the operating system requires to run the main function. By default, GCC will compile and link the binary. It's possible just to compile the .o file and not link it into a binary. Pass the -c flag to GCC to have it generate the main.o file. The LD utility can link the main.o file to create the hello binary. The linker complains that it cannot find the _start symbol or the putS symbol. While you could work out the appropriate syntax for the LD command, the recommendation is not to use it directly. Instead, use GCC to perform the linking. GCC will invoke LD with the appropriate arguments. CLion is another open-source compiler similar to GCC. Install CLion if necessary. For the most part, CLion is a drop-in replacement for GCC. Being a drop-in replacement means that CLion supports most of the same flags as GCC. Compile main.c with CLion. CLion generates different files from GCC, and the assembly language it generates is different. Different compilers often generate different CPU instructions for the same source code. It is essential to use multiple compilers and operating systems to help ensure that your code is portable. Using multiple platforms makes it harder to rely on platform-specific behaviors inadvertently. Anytime a program depends on non-standard behavior, it has fewer chances of running on a new platform. The best time to find a bug is before the program runs. Compilers and other tools can help find potential bugs. This sort of static analysis is crucial, but is something that programmers often skip over. Don't skip out on using these tools. If you do, you will likely waste a lot of time debugging problems that are trivial to solve. The main job of a compiler is to turn source code into instructions that a CPU can execute. Sometimes, code may be syntactically correct but have logic issues. For example, you could call printf with an integer variable with no assigned value. This will work, but depending on the platform, it could print out 0 or a random number. The compiler has enough information to warn about this sort of problem. Most compilers have levels of warnings, such as low, medium, and high. In general, the higher the warning level, the slower the compiler will be. However, these days, most compilers are very fast, and the benefits of finding issues early in development outweigh any time lost. You should spend time to ensure that your code compiles clean, with no warnings. Having many warnings in your code makes it hard to find the critical ones. Spending time keeping your code clean pays dividends, especially as deadlines approach. GCC and CLion have several flags to control warnings. At a minimum, you should use standard equals C17, which tells the compiler to use the latest C standard. WALL, which tells the compiler to enable a lot of common warnings. WExtra, which tells the compiler to enable even more warnings. And WPedantic, which tells the compiler to be extra picky. You can see all of the flags in the GCC manual. Compiling main.c with these flags shows that argc and argv are unused. You have 6 choices. Don't fix the warning, don't pick that choice. Disable the compiler warning, don't pick that choice because sometimes that warning is important. Use an attribute to turn off the warning, don't pick that choice, it's not standard. Pretend to use the variable. Don't pick that choice, it's not obvious. Change the main to accept void instead of argc and argv. Or disable the warning for the main function only. In this case, use a pragma directive to disable the warning selectively. Pragma is a compiler-specific directive. Add the pragma to save the current state of diagnostics. Add the pragma to disable the warning. Add the pragma to restore the state of diagnostics. Now the warning is disabled only for the main function. If a compiler doesn't understand a pragma, it ignores it. Notice that both GCC and CLion support this pragma. Why is using pragma okay, but using void argc or an attribute is not? Pragma is a formal part of the C standard, attribute is not standard, and void argc is not obvious. While it is compiler specific, pragma is clear. Is using pragma ugly? Yes. The fact that pragma is ugly should make you think twice about using it. The better choice, in this case, is for the main function to take void for arguments, which clarifies the programmer's intent. The program has no arguments. Compiler warnings are valuable, but the compiler has a lot of work to do, and its focus typically isn't on warnings. A Lint tool provides a much deeper analysis of the source code. The purpose of a Lint tool is to look at the source code for suspicious code. Source code that passes Lint is less likely to have bugs and be more portable than code that does not. Clang-tidy is an open source Lint tool. Install Clang-tidy if necessary. Clang-tidy has several checks that you can turn on and off. Run Clang-tidy with all the warnings turned on for main.c. -checks =* turns on all of the checks. Clang-tidy complains that the compilation database does not exist. The database informs Clang-tidy about each file's compiler options, which helps Clang-tidy provide better warning messages. Managing a compiler database for a project with many C files can be tedious. Later you will see a simple way to update the database automatically. For now, add a compile flags.txt file that tells Clang-tidy that the language is C. Quiet turns off some of the messages that Clang-tidy reports. The warning about including system headers is not helpful and can be disabled. The compiler already reports the warning about unused variables, so that warning can be disabled too. The source code is free of lint warnings. Later, you may find more warnings you want to turn off. Before you turn off a lint warning, be sure you understand what it means. Compiler warnings and lint are a great way to help reduce bugs in code. However, such static analysis tools cannot find logic errors. A debugger shows the state of a program at runtime. A debugger typically shows things such as the value of variables, the sequence of function calls that have occurred, the current line being executed, the line that a crash occurred on. Another helpful feature of a debugger is the ability to set a breakpoint. Breakpoints are places where the debugger will pause the execution of a program. Stepping from one line to the next is a great way to watch the program flow, seeing what is happening line by line. The GNU debugger, or GDB, is command-based. While the interface is not fancy, it's a very powerful debugger. Compile with the -g flag to embed debugging information into the compiler output. Run GDB. Use the file command to tell GDB what binary to debug. When you compile with -g, symbol information is added. Symbols contain information such as the name, type, and line number for variables and the source code for each line. Set a breakpoint. GDB sets the breakpoint on the first line in the function called main. Run to the breakpoint. The program stopped on the call to display message, which is the first line in the main function. To view the source code, type list. Only being able to see a little bit of what's going on is frustrating. Seeing the source code all the time would be much nicer. Kill the process. Quit GDB. This time, rerun GDB with the terminal user interface. Also specify the name of the program to run. The terminal UI is a simple text-based GUI that shows the source code. Set a breakpoint on line 10 of the main function. Run to the breakpoint. The terminal UI shows the next line to execute. Show the value of argc and argv. You can also list any local variables. Step into the display message function. Check the call stack. BT is short for backtrace. 0 is the current line, main.c, line 18. 1 is where the display message was called from, main.c, line 10. Step again to run printf. You can see Hello World is displayed. Return to the main function. Kill the program and quit GDB. LLDB is a debugger that is part of the same set of tools as CLion and Clang-tidy. While LLDB is similar to GDB, unlike CLion, it is not a drop-in replacement. The concepts and behaviors are generally similar, but the format of the commands differs. Type LLDB hello. Install LLDB if necessary. Setting a breakpoint is different. Running is the same. Stepping is the same. To enter the user interface, type GUI. There are three panes: sources for the source code, variables for the variables, and threads for the call stack. To step out of the function, press F4 and select Step Out. To exit the GUI, press Escape. Kill the process. Rerun the debugger. Unlike GDB, LLDB shows more of the source code. View the args. There are short versions for many commands. Step into the display message function. Look at the call stack. As you can see, GDB and LLDB do similar things in similar ways. The structure of a program is essential. Each function should have a clear purpose. Put related functions into a file with a name that indicates the overall purpose. For example, display.c may have the code for printing things out. Input.c may have the code for reading from the keyboard or files. Network.c could have the code for handling networking. The main.c file should contain the function main. Make a new file, display.c, for the display message function. Compile the files. Function prototypes become very important when you separate functions into different C files. A C file is also called a compilation unit. A compilation unit requires all the information that the compiler needs to compile it. Each C file could provide the function prototypes it needs, violating the principle that you don't put the same code in two or more places. Fortunately, C provides a solution: header files. Make a new file called display.h. A header file contains function prototypes and other symbols that are shared. When a C file needs a function prototype, it includes the appropriate header file. Header files can include other header files. It isn't a good idea to have the same header file appear more than once in a given compilation unit. Use header guards to ensure the contents of a header file are included only once per compilation unit. If and def is false if the compilation unit has not yet seen the name. Define defines a name in the compilation unit. Endif ends the header guard. The header guard ensures that the contents of the header file are included only once per compilation unit. Now the main and display C files can both include the display header file, giving both access to the display message function. Include with double quotes looks in the local directories and then the system directories. Include with angle brackets only looks in the system directories. The system directories contain the header files for things like the standard C library and the operating system. The local directories hold the includes for the project. It's common to put the header files into a separate directory. Make a directory called include. Move the display.h file to the include directory. The compiler cannot find the display.h file because the include directory is not in the list of local directories. Unless otherwise specified, the current working directory is the only local directory in the include list. -i include appends the include directory to the list of local directories. Unfortunately, separating the header file from the C file breaks Clang-tidy. Update the compileflags.txt file to tell it where to find the header files. The -i and the include must be on separate lines. The LLVM include order warns when you include system headers before local headers. As programs get larger, the documentation becomes more important. Ideally, the code should need very few comments. Only hard-to-understand code needs comments. Any code that's hard to understand should be broken up into smaller functions or rewritten to be more straightforward. An API, or Application Programmer Interface, consists of all the function prototypes, variables, and data structures that are available. Always document APIs. Each function should at least have a description of what it does, a description of the parameters it takes, and a description of the return type. This basic information is essential for any developer unfamiliar with the code to help them understand what it can do. The documentation should be straightforward while also being complete. Doxygen is a common tool used for documenting APIs. Install Doxygen if needed. Doxygen uses a configuration file. To generate the configuration file, type doxygen-g. By default, the configuration file is called doxy file. You can see that it has several settings. Set the name of the project. This is version 1 of the project. Give the project a short description. Use Ctrl-W to search. Optimize the output for C. Set Javadoc autobrief to yes. The include directory is where the API will be documented. LaTeX is a document preparation system. You can use it if you want, but HTML is fine. Open the display.h file. Add a document comment before the display message function. Make sure you start the comment with /**. Make sure you end the description with a period. Run Doxygen, passing it the configuration file. To view the documentation, open the index.html file in a web browser. Navigate to Files. Select display.h. You can see the comment. Doxygen can document much more than just the function description, as you will see later. Trying to remember all of these commands and flags and manage everything can be a chore. You could create a shell script to automate these repetitive tasks. However, there's a better solution. Use a build system. A build system automates compiling and other tasks like Lint or Doxygen. A build system is generally intelligent enough to only compile files that have changed. Most importantly, a build system can be shared between multiple platforms and developers, ensuring that builds are repeatable. If each developer were to build the project their own way, it would be hard to ensure that the final product works reliably. There are several build systems available. The Make utility provides a simple yet powerful build system. Make reads a makefile, which contains a set of targets. A target has a set of dependencies and commands. When you run the Make utility, it searches for a file named makefile. Create a file called makefile. Putting .posix at the top of the file helps ensure that the makefile is portable between different implementations of the Make utility. Portability is not guaranteed, so you should test your makefile on each platform early in development. Add a target called hello that depends on main.o and display.o. Use GCC to link the files into a binary called hello. Ensure that you use the tab key to indent. Spaces will not work, and the error message may not be clear. Add a target for main.o that depends on main.c and display.h. Use GCC to compile main.c to main.o. Add a target for display.o that depends on display.c and display.h. Use GCC to compile display.c to display.o. Any developer on any distribution can use the makefile, which should reliably reproduce the build steps. See that the main.o, display.o, and hello files were all created as expected. By default, Make uses the first target in the makefile. In this case, the first target is hello. You can also specify a target explicitly. Nothing happened. The binary is newer than the source and header files, so Make has no work to do. Update the display.h file. Run Make again. It rebuilds all of the files. Make runs the commands for any target where the dependencies have changed. Add another target, clean, with no dependencies. Use the rm utility to remove the transient files. Make deleted the files as expected. Clean the project again. The error occurs because RM failed to delete one or more files. Add the -F flag to RM, which tells RM not to fail if some files do not exist. Make will be confused if a target, such as clean, has no parameters and a file with the same name as the target exists. Adding .phony resolves the confusion. Add another target, called all, that depends on the hello target. Running clean all is known as a full rebuild. You can still run targets independently. It's a good practice to do a full rebuild periodically to ensure that the compiler hasn't accidentally forgotten to recompile something. Makefiles can use variables. Create variables for the object files and the binary. Make has several built-in variables. Some of them are: CC is the compiler, allowing switching between GCC and CLang. C flags are the compiler flags. LD flags are the linker flags. LD-libs are the libraries to pass to the linker. The default value on my system for CC is user bin C99. Set the CC variable to GCC. Convert as much of the makefile to use variables as possible. Variables make it easier to maintain a makefile. Save the makefile and do a full rebuild. The command line can override variables in the makefile. Rerun make with cc equals CLang. This time, make compiled with the CLang compiler. Unfortunately, a standard makefile doesn't have a way to append a variable set on the command line. Adding C flags is not as simple. Set C flags all with C flags prepended. Run make passing the -g flag. The -g flag is passed to the compiler along with all the other flags. Having to write the same compiler line repeatedly is error-prone. Suffixes are automatic rules to transform one type of file into another. Turn off the default suffixes. Inform the makefile that the .c and .o suffixes exist. Add a suffix to convert C files to O files. Move the compiler line to the suffix for C to O. $@ is the name of the .o file. $less than is the name of the .c file. From now on, any new .c files only need to state their dependencies. Other programs, such as Doxygen and Clang-tidy, can be added to the makefile. Add variables for Doxygen. Add docs to the target all. Add the docs target. Doxygen generates the HTML index.html file. If the HTML index.html file is older than the source files, header files, or the doxy file configuration file, then Doxygen must run. The Doxygen utility is very verbose. Edit the doxy file to turn quiet on. Clean does not remove the HTML directory. Add -r to rm so that the HTML directory also gets deleted. Add the HTML directory to the clean target. Set up Lint. The lint target can run whenever you want, Adding lint to the all target causes Clang-tidy to run, even if there are no changes to any source files. As a workaround, add lint after linking. You can quickly build the source code, run lint, and generate the documentation all with one command. And when any file changes, the right things are rebuilt, and always runs when the source code changes. CMake is another build utility. CMake is not a build system itself. Instead, CMake generates files for a build system, such as a make file for Make. Install CMake. A typical CMake project separates the source files and the header files. The make file no longer works because of the subdirectory. Move it somewhere safe. Similar to Make, CMake reads a configuration file. The file must be named CMake lists.txt. Set the minimum CMake version required to run the CMake lists.txt file. Newer versions of CMake support additional features. Match it to the version of the installed CMake. You may need to lower the version number later, depending on your platforms and what version of CMake they have available. Provide information about the project. Some compiler flags, such as the version of the C standard to use, are abstracted, which means that CMake can set the value for any compiler. Other flags are not abstracted. Add the executable and its dependencies. Add the include directory. Unlike Make, CMake can build the files into a subdirectory. Run CMake telling it the source and build directories. -S sets the source directory, -B sets the build directory. It is important to rerun this command whenever the cmakelists.txt file changes. Run CMake to build the project. Add the clean first flag to do a full rebuild. Switch compilers by setting the CMake C compiler variable on the command line. You may find it helpful to have different build directories for various compilers. Naming the directories helps you know which compiler built the code you were running. You can pass C flags on the command line too. CMake has variables. Add variables for the header and source files. Update the executable. Save, exit, and rebuild the project. Rebuild the binary. If you look at the build directory, you will see the make file that gets generated. Remember that CMake is not a build system. CMake is a utility for building the files that a build system, such as Make, needs. CMake can integrate Doxygen. Find package tells CMake to find the installed version of Doxygen. I've configured it so that the Doxygen utility must exist on the system or CMake will not run. Set the configuration file to use. Add the custom target so that the Doxygen utility will run. Now when you make a build, the API documentation is generated too. CMake can integrate Clang-tidy. Clang-tidy must be installed on the system. Auto-generate the compilation database. Turn all the checks on. Set the command to run. Add Clang-tidy to the build. Look in the build directory at the compile commands JSON file. Imagine having to maintain the compiler database by hand for hundreds of files. Notice it is a transient file. Due to the absolute paths, it will likely be different for every developer. Now that you have the compiler database, you no longer need the compile flags.txt file. Selectively turn off the warnings that are not wanted. Remember that every time CMake lists.txt changes, you must remake the build system. You may be wondering if you are stuck on the command line and using cryptic debugging tools forever. The answer is no. Soon you will see more modern tools that you can use if you wish. The modern fancy tools are generally built on the command line tools you've worked with up to this point. It is essential to understand the pieces and how they work. The command line is powerful and lets you do many things, but sometimes it's not the most convenient way to work. An integrated development environment, or IDE, is a tool that typically brings together an editor, compiler, lint, build system, debugger, and other tools. A modern IDE typically provides a friendly user interface. Remember that underneath the fancy UI are the same command line tools you have used until now. Integrating all of these tools can speed up the development process. CLion is a cross-platform graphical IDE made by JetBrains that supports C and C++. CLion is free for academic use. CLion is not the only IDE available for C development, but it is what I use. You can install CLion itself or the Toolbox app, which makes installing other JetBrains products easy. Install the Toolbox app. Start the Toolbox app. Set up the Toolbox app. Install CLion. You will need to log in. Create an account if needed, or log in. Start CLion. CLion is project-based, meaning you create a project containing your source code and CMake lists.txt. You can make a C executable or C library. You can choose the language standard you want. If you were to make a library, you could choose to make it static or dynamic, also known as shared. Each project must be in a separate directory. CLion has an editor, performs Lint on the fly, uses CMake for building, and provides a nice front end for GDB or LLDB. Run the project by pressing the Run button. The output appears in the output pane. Close the project. Open the project you've been working on throughout this video. While you have not been working on a CLion project, you have been working on a CMake project. And remember, CLion uses CMake for building. Run the project. CLion provides a graphical debugger. Remember that most debuggers have the same general functionality, but how you access or view it differs. Open main.c. To set a breakpoint, click on the margin. To remove a breakpoint, click on it. Set a breakpoint on the display message call. Run the debugger. You can see the call stack and variable values in panes, similar to the LLDB GUI. Access the stepping functionality with the keyboard, buttons, or menu. Press the stop button to kill the debugger. As you will see later, stepping is an excellent way to understand how code works.